Welcome viewers. Today we are discussing functions of complex variables. In this lecture I will be covering function of a complex variable, then I will introduce the concept of limit, I will continue with continuity of a complex variable, then I will introduce analytic function, and finally we discuss harmonic functions. First, function of a complex variable. Let x and y be real variables, then we denote z as x plus iy, and we say that z is a complex variable. We know that x and y, they are real variables, they lie in an open interval of real line. Then function of a real variable x is defined over an interval a b. However, z will lie on some region S of complex plane and S is a subset of z. Now we are in a position to define the function f of a complex variable such that it takes values on the set S and will map to the complex plane z. Then w is a function of z, where z belongs to the set S. In such a situation we say that f is a function of complex variable z. Let me illustrate this on this diagram. We have a real variable x, it lies in interval a b, and this is the part of the real line. This is another real variable y, and the variable y will lie on this line, and the z will be lying on this plane. This plane is called z plane, while a point on z plane will map to a point on w plane such that w is equal to fz. Now the values z can take in this domain, we call that domain as S. So S will map to z and we say w is a function of z. This plane is x and y, while this plane is called w plane. Here z is x plus iy, while when it mapped to w, then w is written as u plus iv. So this is real line u and this is real line v. The correspondence between points in the two planes is called a mapping or a transformation of points in z plane into points of w plane by this function f. So that is how we introduce concept of functions. Let u and v be real and imaginary part of w, then we write w is equal to fz is equal to u plus iv. Normally u is a function of x and y and v is also a function of x and y. So w also has a real part u x y and imaginary part v is also a function of x and y. So in this sense, complex function fz is equivalent to two functions u of x and y and v of x and y. For example, we write w is a function of fz, which is defined as 2z square plus 3z plus 5. So if I write z is equal to x plus iy, then it is 2 multiplied by x plus iy square plus 3x plus iy plus 5. Simplifying this, it is 2 x square minus y square, the real part coming from this expression, and then plus 3x plus 5, and then I times 2xy coming from this plus 3y is the imaginary part. So this way we write the function w as consisting of real part as uxy is equal to 2 times x square minus y square plus 3x plus 5, and the imaginary part vxy is 2xy plus 3y. This is another example. Here we write the function fz as modulus of z and we write it as under root of x square plus y square x and y being the real and imaginary part of z. Fz is a real valued function of a complex variable because this function does not have an imaginary part. So, Fz maps to real value, that is why we say this function Fz is a real valued function of a complex variable z. Normally, the mappings of curves and regions usually displays more information than mappings of individual elements. So, under this mapping we write what a particular point will map to this particular point. A particular point in z plane will map to a point in w plane, but it is more meaningful if I say this circle mod z is equal to 5 will map to this point in the w plane. So, this boundary will map to w plane. So, normally mappings of curves and region, they display more information rather than mapping of individual elements. Now, we will discuss elementary functions of complex variables. We have functions of real variables, we extend those functions to complex variables in such a manner that when we consider the variable to be a real variable, they will become function of a real variable. So, it is simply an extension from real domain to complex domain. So, let us say Fz is a function of z raised to power n is a positive integer. We define this function as z times z raised to power n minus 1. The idea is it is repeated multiplication, and when z is a real variable, then f of x becomes x raised to power n. With this, z square means z multiplied 2 times, z raised to power n means z is multiplied n times. Now, z raised to power n can be written as x plus iy raised to power n, and x plus iy in polar form can be written as r cos theta plus I sin theta. Also, in this sense, this number, this x plus iy raised to power n is r raised to power n multiplied by cos theta plus I sin theta raised to power n, and further this can be simplified to r raised to power n cos n theta plus I sin n theta. So, z n can be expressed as real part r n cos n theta plus I times imaginary part r n sin n theta, where the real part u is function of r n theta and imaginary part is also a function of r n theta. Once we have defined z raised to power n, we are in a position to define polynomial function. So, polynomial function is a linear combination of powers of z, and we write it as a naught plus a1 z plus a2 z square plus a n z n, where a n is not equal to 0. So, it is a linear combination of powers of z, means we have z raised to power 0, z raised to power 1, z square, z n, and then we have taken their linear combination, that is each term is multiplied by a constant and then added. Here it is noticed that n is not equal to 0. By this I mean to say that this is a polynomial in degree n. If a n is equal to 0, then this polynomial will be of lower degree. In short, we write the polynomial p z as summation I is equal to 0 to n a I z I, and this I will take values from 0 to n. From here we extend to a rational function. A rational function is defined as a ratio of two polynomials. So, if I have two polynomials p and z and q m z, then w is p and z divided by q m z. Normally these n and m are different, but they may be same. Here you may note, here the important thing is that q and z is not 0. The power series of a complex series is obtained as limit of pz as n tends to infinity. So, we write this expression as pz is equal to limit of ai zi n tending to infinity. So, this becomes a power series, and we write it as sz is equal to a naught plus a1 z plus a2 z square plus a n z n and so on. So, this is a power series. We call it a power series because each and every term is expressed as some power of z. Next is limit of a function of a complex variable. Before we proceed to limit of a function of a complex variable, I like to review the concept of limit in case of real valued functions, real variables. So, limit of a function of a real variable, let f x is a function of a real variable x, then we say that L is the limit of this function f x as x tends to x naught if f x is defined in the neighborhood of x naught except possibly at x naught, and then for every real number epsilon there exists a delta such that for every x not equal to x naught we have x minus x naught less than delta implies f x minus L is less than epsilon. By this I mean to say that whenever we are close to x, then we are close to L also. So, if we are close to x naught and the distance between x and x naught is delta, then there will be some epsilon and will be close to f x, the function f x will be close to L. So, that is the meaning of limit of a function of a real variable. Closeness to x means closeness to L. Now, with this we will go to limit of a function of a complex variable. So, let us say f z is a complex variable function, z is the complex variable, then this function f z has a limit L as z tends to z naught if it satisfies the two conditions. The first is f z is defined in the neighborhood of z naught except possibly at z naught. Further, for every real number epsilon which has to be positive, there exists a positive delta such that for every z not equal to z naught we have modulus of z minus z naught is less than delta implies modulus of f z minus L is less than epsilon. This z minus z naught modulus less than delta represents a unit circle centered at z naught and of radius delta, while f z minus L modulus less than epsilon represents a circle centered at L and of radius epsilon. So, that means whenever we have points in this circle in z plane, then we will have points in the circle in w plane. Let me illustrate this pictorially. So, let us consider z plane and w plane. In z plane I have a point z naught and there is a mapping which maps f of z naught to L. So, we consider all the points in the delta neighborhood of z naught. So, whenever we take a point in this neighborhood, so this is a circle of radius delta centered at z naught, this is a circle of radius epsilon and centered at L. So, whenever we have a point in this neighborhood of z naught, then correspondingly we have the point f of z in this circle. So, points here will map to points here. So, points in the delta neighborhood of z naught will map to points in the epsilon neighborhood of the limit L. That is the meaning of limit of a function f of z, and this we write it as limit of f z as z tending to z naught as L. In case of real variables, we have left hand limit and right hand limit of a function. However, in case of complex variables, the concept of limit is more general and we will not have only left hand limit and right hand limit. We have two limits in case of real variables because we can approach to the point from left side or from the right side. because the function is defined on an interval. But in case of complex variables, we can have infinitely many paths to approach to the given point z naught. So, in this sense, all the limits from all the paths should be equal, and we say this concept is more general in case of complex variables. A function f z is said to be continuous at the point z is equal to z naught if f z naught is defined and limit of f z as z tending to z naught is f of z naught. Now, this definition is also an extension of the definition of continuity of continuous functions of real variables. And then a continuous function is one which is continuous at all points of its domain. After defining limit and continuity of a complex variable function, we are now in a position to define differentiability of a complex variable function f of z. A function f z is said to be differentiable at z is equal to z naught if limit of the expression f z naught plus delta z minus f of z naught divided by delta z as delta z tending to 0 exists, and then we say this limit is f dash of z naught or derivative of f at z naught. If I denote z naught plus delta z as z, then this expression can be written as f of z minus f of z naught divided by z minus z naught. The limit of this expression as z tending to z naught is defined as f dash of z naught. Since we are defining limit here, so if we apply the concept of limit, then f z minus f z naught divided by z minus z naught minus f dash z naught, its modulus is less than epsilon whenever z minus z naught modulus is less than delta. The derivative, or we call it as differential coefficient of a function w of f z is denoted by dw by dz. So, this is nothing but dw by dz, and we write dw by dz is limit of delta z naught tending to z as delta w by delta z. We say this is the change in f divided by change in z. So, this is delta w divided by delta z. When delta z tending to 0, it is called dw by dz. Let us illustrate this with an example where f z is equal to z square. So, if we have to differentiate this, then d by dz of z square is equal to z plus delta z whole square minus z square divided by delta z. So, this is the ratio we form, and then we take the limit as delta z tending to 0. So, when we simplify the numerator, this comes out to be z square and z square cancels out, and what we have is 2z into delta z, which will cancel with this, plus delta z square, which out of this delta z square, this delta z will cancel out and we will have only delta z. So, limit of 2z plus delta z as delta z tending to 0 means this is nothing but 2z, or we say the derivative of f z is 2z. Now, we form the rules for differentiation of a complex variable. These rules are very similar to what we have for real variables, and their proof are also very similar. So, one by one, powers of z, that is z raised to power n, derivative of z raised to power n is nothing but n times z raised to power n minus 1. Then we can have derivative of sum of two functions f z plus g z, then derivative of this sum is sum of derivatives. Similarly, we can write down a formula for product of two functions. Then when we have ratio f z divided by g z, we can differentiate them provided g z is not 0. then we have chain rule, and it is a composite function. Similar formulae can be obtained for these cases when we have a function of a complex variable, and they can be used in this example. So, if we have to find the derivative of 3z raised to power 4 plus 2z square plus 5. So, we can consider it to be sum of 3 functions 1, 2 and 3, and the derivative will be derivative of this plus derivative of this plus derivative of this. We know how to find derivative of z raised to power 4, and we know how to find derivative of z square and so on. So, the derivative of this can be easily formed. Similarly, in this expression it is z minus 3 raised to power 4. So, write down the derivative, it is a composite function. So, we can find out the derivative of z minus 3 raised to power 4. So, if we solve this, the derivative of this function f dash of z is 12 times z cube plus 4 times z, and derivative of 5 is, derivative of constant is 0. And in the second case, f dash z is 4 times z minus 3 cube into derivative of z minus 3, which is 1. So, derivative of this function is simply 4 times z minus 3 cube. Now, we introduce the concept of analyticity. A function f z is said to be analytic at a point z naught if it is defined and has derivative at every point in some neighborhood of z naught. So, basically when we say differentiability, a function is differentiable at a point, but when we talk about analyticity, it has to be differentiable not only at a point z naught, but it has to be differentiable in some neighborhood of z naught. Example, the function f z, which is equal to x minus I y, is not differentiable anywhere. Let us check this. F dash z is obtained as limit of this ratio. This is delta z, delta of f. So, function f is z bar, x minus I y is z bar. So, z plus delta z bar minus z bar divided by delta z, and then we take the limit as delta z tending to 0. So, this is nothing but delta z bar divided by delta z, and this is equal to limit of delta x plus delta x minus I times delta y, because we are taking conjugate. So, it is delta x minus I times delta y divided by delta z, which is delta x plus I times delta y. So, to take this limit, what we do is, we are here, this is my point 0 and this is the point delta z. Now, I can approach to this point in number of ways. To get this limit, what I will do is, I will first take this path. On this path, first we have delta y drop to 0 and then delta x is tending to 0. So, if I take delta y is equal to 0 in this expression, then this and this will cancel out and they will be 0, and what remains is delta x divided by delta x, which is 1. So, whenever delta x tending to 0, this expression gives me limit as 1. So, on path 1, limit of this expression, that is f dash z, is equal to 1, while if I consider the second path on which delta x is dropped to 0 and then delta y is tending to 0. So, on path 2, when this happens, that means delta x they become 0 and delta y tending to 0. So, this and this are equal. So, this ratio becomes minus 1, and when we take the limit delta z tending to 0, this remains minus 1. So, we see that along this path limit comes out to be 1, while along this path limit comes out to be minus 1. But from the definition of limit, both the limit should be the same in whatever way we approach to the point z. So, in this sense we say limit does not exist. So, f dash z does not exist, and this is true for all values of z, and that is why we say this function is not differentiable anywhere. Now, this given fz is not differentiable anywhere. So, there is no question that it will be analytic. So, we say fz is not analytic anywhere. Now, we discuss Cauchy-Riemann equations, and these equations they are required for checking the analyticity of a given function. So, first state the Cauchy-Riemann equations and then we will prove it. So, let fz is analytic in a given domain D of z plane, and we write the given function f of z as u x y plus I v x y. So, that means u is the real part and v is the imaginary part. Then f dash z is equal to f z plus delta z minus f z divided by delta z. The limit of this ratio is f dash z by definition of differentiability. So, we write down f dash z as limit delta z tending to 0, and f z plus delta z is written as u x plus delta x y plus delta y plus I v x plus delta x y plus delta y. So, this is a function of this is written as u plus I y, this is written as u plus I v. So, this is the u part and this is the v part. Similarly, f z is u plus I v. So, this is the u part and this is the v part, and here x is a function of x and y and we are giving increment. So, x plus delta x and y plus delta y, but here we have only x and y. So, I have written this into two parts, first the real part and the second is the imaginary part of f. Now, to take the limit I again consider two paths, first the path 1, that is this green path on which delta y is 0 and delta x is tending to 0. So, along this path f dash z is written as u x plus delta x comma y minus u x y divided by delta x and delta z tending to 0, and delta z tending to 0 means delta x is tending to 0. Then limit delta z tending to 0 for I v x plus delta x comma y, delta y is set to 0 minus I v x y divided by delta x. And then we know from the definition of, see, u is a real variable function of two variables x and y, and this is nothing but the definition of partial derivative of u with respect to x, and this is partial derivative of v with respect to x. So, using that definition we can write f dash of z is equal to delta u by delta x plus I times delta v by delta x along this path 1. Similarly, on path 2 delta x is set to 0 and delta y tending to 0. So, if we proceed on same lines, then f dash z comes out to be minus I times delta u by delta y plus delta v by delta y. So, here I have obtained the limit of two expressions, one along this path, another along this path, and we have seen along one path it comes out to be this, on the other path it comes out to be this. If limit has to exist, then both the limits should be same. So, if we compare these two expressions, then for equality of them we should have delta u by delta x, the real part of this must be equal to the real part of this, it is delta v by delta y, and the comparing the imaginary part here and the imaginary part here, it is delta u by delta y is equal to minus delta v by delta x. Now, these conditions are called Cauchy-Riemann conditions. With this, we are now in a position to state the theorem. It says that the real and imaginary parts of any analytic function f z is equal to u x y plus I v x y satisfy the Cauchy-Riemann equations at every point where the function is analytic. Now, these Cauchy-Riemann equations are necessary these Cauchy-Riemann equations are necessary for function to be analytic. Now, the second theorem states that these conditions can be made sufficient. So, according to this theorem, if two real valued functions uxy and vxy have all four partial derivatives continuous and satisfy CR equations in some domain D, then the complex function fz, which is equal to u plus iv, then it is analytic in D. So, we require only the continuity of four partial derivatives together with CR equations, then they imply the analyticity. So, in this sense CR conditions are necessary and sufficient. X plus I delta y plus beta 1 delta x plus delta 2 times I delta y. So, this is nothing but delta z. So, this delta f by delta z is nothing but delta u by delta x plus I times delta v by delta x plus delta 1 times delta x by delta z plus delta 2 I delta y by delta z. And since delta x by delta z, what is delta z? Delta z is delta x square plus delta y square. Delta z square is delta x square plus delta y square. So, delta x is always smaller than delta z, and that is why delta x by delta z modulus is less than equal to 1. Similarly, delta y by delta z is also less than equal to 1, and in this, taking the limit as delta z tending to 0, we will have this becoming df by dz is equal to, this is delta u by delta x plus this becomes delta v by delta x and plus delta 1 delta x by delta z plus delta 2 I delta y by delta z, and they tend to 0, and that is why we say derivative exists, and when derivative exists function is analytic. This is coming because the derivatives are, these derivatives are continuous, and that proves the second theorem. Now, the Cauchy-Riemann equations which we have developed, they are in Cartesian form. When we write z is equal to x plus iy, when we write down the function z, when we write down the variable z as r e I theta, then Cauchy-Riemann equation, they are in polar form. So, to develop Cauchy-Riemann equation in polar form, what we do is we consider z plane, and this is our point z and this is the increment here. So, if you have to take limit from this point to this point, then any number of paths can be taken to approach to this point, but if I consider two different paths, one is along this polar, one along this circular path and then on radial line, that is path 1, and the other path is you move along the radial line first and then on this circle. So, you can approach from this point to this point in two different ways. So, if I consider these two different paths, I get the value of, I get the limit, and when the two limits are equated, what I get is CR equations in polar form. So, let us consider fz is equal to u r theta plus I v r theta, and then I write f dash z is equal to u r plus delta r theta plus delta theta minus u r theta, and this is delta r is written as r plus delta r e I theta plus delta theta minus r e I theta, this is nothing but delta z. Similarly, I write down the second component and then I take limit along two different paths. On path 1, delta theta is 0 and delta r tending to 0, we got this expression, and from here we can easily see that f dash z comes out to be e I theta delta u by delta r plus I times delta v by delta r. Similarly, on the path 2, delta r is equal to 0 and delta theta tending to 0, and we simplify the expression in this form, and from here we will get f dash z as this. So, f dash z on path 1 is this, f dash z on path 2 is this, and from here we can have delta u by delta r is equal to 1 over r delta v by delta theta, and from the imaginary parts we will get delta v by delta r is equal to minus 1 upon r delta u by delta theta. These are polar forms of CR equations. These are the Cartesian form of CR equations. CR equations, we say this is the short form of Cauchy-Riemann equations or Cauchy-Riemann conditions. So, if a function is given f z is equal to mod z square and we have to see what is its derivative at a given point z is equal to 0, then we can make use of the definition of the derivative and we can find its derivative. So, let us compute the derivative using the basic definition. So, f dash z is limit of delta z tending to 0 modulus of delta z square over delta z, and modulus of delta z square I can write it like this, and this delta z and this delta z they will be cancelled out, and what we have is that f dash z is equal to 0. So, and this is independent of path, whatever path we choose delta z tending to 0, this limit will be 0. So, we can say that f z has derivative only at z is equal to 0. This will happen only for z is equal to 0, but at no other point this will happen, and we say this function has derivative at z is equal to 0, but it is not analytic at z is equal to 0. If we have to show that this function is not differentiable at any point, we consider its real part as u is equal to 2x and v is equal to xy square. Then we apply Cauchy-Riemann equation, and from here we get ux is equal to, ux means partial derivative of u with respect to x, it is 2, and partial derivative of u with respect to y is 0. For this, partial derivative of v with respect to x is y square, and for this partial derivative of v with respect to y is 2xy, and one can notice that these CR equations will not be satisfied at any of the points. So, we can say the function is not differentiable at any point in the domain. So, CR equations are not satisfied, one can very easily check, and derivatives from two different paths are different because conditions are not satisfied, and that simply means that function is not differentiable. In next example, you have to show whether function is analytic or not. So, we consider f z is equal to E x cos y plus I sin y. So, accordingly u is equal to E x cos y and the imaginary part v is equal to E x sin y. We calculate the various derivatives, u x is equal to E x cos y plus v y is E x cos y, and we can see that u x is equal to v y. Similarly, when you calculate u y and v x, both the derivatives comes out to be satisfying this condition. So, all the CR conditions are satisfied and it is irrespective of whatever be the value of x, these conditions are satisfied, and we say that this function is analytic. Moreover, these functions, these partial derivatives u x, v y and u y and v x etc., they are continuous. So, by the help of the two theorems which we have established, we can say that this function is analytic. So, all these things I have already explained. So, this given function is analytic. Now, this example make use of CR conditions in polar form. So, the question is the following function analytic or not. So, f z is equal to log r plus I theta. So, accordingly u is equal to ln r and v is equal to theta. We make use of polar forms of CR equations which are given as this, and one can check that these conditions are satisfied. This is straightforward. So, function is analytic. Now, in this case you have to check the analyticity of the function f z is equal to z plus z bar. We write down f z is equal to z plus z bar as x plus I y plus x minus I y. So, this comes out to be 2x, and accordingly this function has u is equal to 2x while v is equal to 0. So, when we calculate various partial derivatives, u x comes out to be 2, u y is equal to v x is equal to v y is equal to 0, all other derivatives are 0. So, this u x is equal to 2 and v y is 0. So, this condition will never be satisfied. So, CR conditions are not satisfied and this function is not analytic. In fact, we can say CR condition is not satisfied, function is not analytic, and we say that any function of z bar is not analytic. Any function which involves z bar, that function will not be analytic. Like in this case, the function is written as z plus z bar, so this function is not analytic. Let f z is equal to u x y plus I v x y be an analytic function, then CR conditions are satisfied. That means delta u by delta x is equal to delta v by delta y, and delta u by delta y is equal to minus delta v by delta x. And when you differentiate this first equation with respect to x partially, then left hand side is delta 2u delta x square, while right hand side becomes delta of delta x of delta v by delta y. And similarly, we differentiate the second equation partially with respect to y. So, left hand side gives me delta 2y delta y square is equal to minus delta y of delta v by delta x, and we have two equations. If we add them together, this becomes delta 2u delta x square plus delta 2u delta y square, and since these derivatives are continuous, so we can say that delta by delta x of delta v by delta y is the same as delta by delta y of delta v by delta x. So, they will cancel out, so right hand side will be 0. Now, this is the Laplace equation in two variables x and y. So, we say u satisfies the Laplace equation in two variables. Similarly, the other partial derivative, other function v also satisfies the Laplace equation. So, what we can do is we first differentiate the first equation by we first differentiate with respect to delta by delta y, we get this expression. In the second equation is partially differentiated with respect to x, we get this. When you add the two, we will have delta 2v delta x square plus delta 2v delta y square equal to 0. And this means that the real and imaginary parts of an analytic function in a domain D are solutions of Laplace equation. This is an important result, and on the basis of this we say that a harmonic function has continuous second order partial derivatives that satisfy Laplace equation. So, we define a harmonic function which satisfies the Laplace equation and has second order continuous partial derivatives. That means, the analytic function, the real and imaginary part of an analytic function will be harmonic functions. This is what I have stated. The real and imaginary parts of an analytic function in a domain D are harmonic functions. So, if u and v are real and imaginary parts of an analytic function, then they are called conjugate harmonic functions. And finally, the functions u and v define a pair of conjugate harmonic function. We say u is conjugate of v and v is conjugate of u, and this says that u and v will define a pair of conjugate harmonic functions. So, given a harmonic function, we can always find its conjugate harmonic function. So, if u is given, then using CR equations we can find v, and if v is given we can find u. This we do in this example. Here function u is given as ln x square plus y square. First we have to show that this function is harmonic, and then we have to find its conjugate harmonic function. So, to show that this function is harmonic, one has to show that it satisfies the Laplace equation. For this, u is equal to ln x square plus y square. So, we calculate the derivative ux, which comes out to be 2x divided by x square plus y square, and its second derivative uxx, if you differentiate it once again, then it is 2 times x square plus y square minus 2x times derivative of this, it is 2x. So, this is the numerator divided by denominator square x square plus y square whole square, that comes out to be the second derivative of u. Simplifying this, uxx comes out to be 2y square minus 2x square divided by x square plus y square whole square. On the same lines, one can differentiate this expression partially with respect to y. that gives me uy as 2y over x square plus y square, and again differentiating partially with respect to y gives me this expression for uyy, and when you add the two, uxx plus uyy, this comes out to be 0. That simply shows that u satisfies the Laplace's equation, and that shows the first part, that u is a harmonic function. Once it is established that u is a harmonic function, we can make use of CR equations to find its conjugate. So, ux we have already computed, this will be equal to Vy according to CR equations. So, Vy is 2x over x square plus y square. Similarly, Vx will be minus of Uy, which we have computed as this. So, using CR equations, I have expressions for Vy and Vx. Now, this can be integrated partially with respect to y. See, it is a partial derivative with respect to y. So, I am treating x as constant while I am getting the derivative. So, to get v from this expression, what I have to do is I have to integrate this expression with respect to y, keeping x fixed. So, when I integrate this, I get Vxy is equal to 2 times tan inverse y by x plus constant of integration. Now, normally we have to have a constant of integration C1, but in this case I am getting a constant, instead of having a constant I am writing C1 as a function of x, because in this integration I am treating x as a constant. Similarly, when you integrate this partially with respect to x, we will have Vxy is equal to minus 2 tan inverse x by y plus C2y. So, if we compare these two, we will say that Vxy is equal to 2 theta. This C1x and C2y, they should not be functions of x and y. So, we have Vxy is equal to 2 theta. So, once we have obtained Vxy is equal to 2 theta, I can write down the analytic function fz as ln x square plus y square, the real part, and this is the imaginary part. So, it is 2I theta. So, my analytic function is this. Next, we will discuss application of complex variables to potential problems. The real and imaginary parts of an analytic function are solution of Laplace equation in 2 dimensions. This is what we have seen just now. Now, the conjugate functions provide solution to a number of potential problems. In these problems, the physical quantities are obtainable from a potential function which satisfies the Laplace's equation. Now, there may be number of problems, but I will be considering a problem from fluid flow. So, consider 2-dimensional irrotational motion of an incompressible fluid. To explain this, the motion is said to be irrotational when curl of V bar is equal to null vector. From differential calculus, we say that V bar is equal to grad of phi. V bar is the velocity field here, velocity of fluid flow. Then this suggests that Vx, the x component of velocity, will be delta phi by delta x, and Vy, the y component of velocity, will be delta phi by delta y. Now, such a function phi is called the velocity potential, and we write velocity V bar as x component in the I direction plus y component in the j direction. So, we write V bar as Ivx plus jVy. So, Vx and Vy are functions of x and y only, because we are considering 2-dimensional flow. So, they are functions of x and y only, no more z is involved in it. When the fluid is incompressible, its divergence is 0. So, this gives divergence V bar is equal to 0, or delta Vx over delta x plus delta Vy over delta y is 0. And since Vx is equal to delta phi by delta x and Vy is equal to delta phi by delta y, that is what we have assumed, then we can substitute these Vx Vy in this equation, and we have delta 2 phi delta x square plus delta 2 phi delta y square is equal to 0. In other words, we say that the velocity potential phi is an harmonic function. So, if it is an harmonic function, then we can associate a function f z which is expressed as phi x y plus I psi x y. So, f z is an analytic function in which the real part is the velocity potential phi, but the question is what is this function psi? We consider the slope at any point of the curve psi x y is equal to c, and it is computed as dy by dx is equal to minus delta psi by delta x divided by delta psi by delta y, which is equal to delta phi by delta y divided by delta phi by delta x from Cauchy-Riemann equations, and this is equal to Vy by Vx. So, dy by dx is this. So, we say that the resultant velocity of a particle is along the tangent to the curve psi x y is equal to c. So, we say that a fluid particle moves on the curve psi x y is equal to 0 and its velocity is given by phi x y. These curves are called streamlines, that is psi x y is equal to c curves are called streamlines, and psi x y is called a stream function. Phi x y is equal to another constant c dash are called equipotential lines. The two curves intersect orthogonally, that can easily be checked. The choice of the function f z depends on the boundary conditions. Since the flow cannot cross a boundary wall, the boundary must be a streamline, and on the basis of this we can solve fluid flow problems. So, if we consider flow at a corner, then the flow in a channel bounded by the axis and the hyperbola x y is equal to a square. Any two of the streamlines could be taken as the boundary walls of the flow, and then f z is equal to phi plus I psi is equal to x square minus y square plus twice I x y, and this function is nothing but z square. So, what I have done is, here I have a corner which is given by coordinate axis, and this is the boundary 2 x y, it is nothing but a hyperbola. So, the flow is between these boundary, this boundary and this boundary, and inside this boundary the streamlines are moving along these curves, and velocity potential will be given by x square minus y square. So, these are again these gives us equipotential lines. So, if you draw hyperbolas x square minus y square is equal to a, then they give us the velocity potential. So, we can see that if the fluid is flowing inside this region, then any particle of the fluid will follow one of these paths. So, that is how we apply theory of complex variables to solve real life problems. So, with this we have completed this lecture on function of complex variables. In this lecture I have started with the very definition of the function, then I have introduced the concept of limit, and this is done on the basis of what we already know, function of a real variable, and then we have extended the ideas. Then we have discussed the continuity, after that the differentiability, and then I have discussed the notion of analyticity of a complex variable. I have obtained CR equations for checking analyticity of a function. I have given some examples to illustrate the concept of analytic function, and then I have introduced the harmonic function, and then some problem and its applications to real life problems. That is all for today's lecture. Thank you.
Thank you.